Now, we saw volumes as an application of integration previously, and all we really had to know was pi times the integral of y squared or x squared, depending on whether we were going around the x or the y axis. In extension 2, we look at it in a little bit more detail and we see, where does this come from, and can we then use this idea for shapes that don't have circular cross sections? Because that's terrific if it's got a circular cross section, but what about other shapes? I mean, there's lots of other shapes around as well. So to start off with, we're going to look at what we already know, but approach it from the actual ground up. First principles, as they say, the first idea. So this is what we call slices perpendicular to the rotation. So if I'm going around the x-axis, here's our random curve, and I want to rotate a section of that curve around the x-axis. And the idea, and you'll remember from when we first started integration, we talked about areas, and it was the sum of all the areas of these rectangles, and we wanted to make those rectangles as thin as possible, and that all got us to our first derivative formula and so on. So it's the same sort of idea. There's that one of those rectangles, or what we now call a slice, and we're just going to rotate that slice. Now, when we rotate that slice around the x-axis, we get a disc, or a cylinder if you like. And we know the formula for a volume of a cylinder. And so then what we do is we want to add up all of those cylinders. So my radius for this would be whatever the y value is. And I'd say, well, all right, that y value, I actually want it in terms of the thickness. Now, the thickness is the change in the x value. So I don't want y, I want whatever function x is, whatever y equals. I want it in terms of the x value. So it'll be pi times function x squared is the face of the cylinder or the circle. So to work out the volume then, or the change in volume, would be that area times whatever the thickness is, whatever the change is, the height of the cylinder if you like. Now that's what we call the element of the volume. So that's the element. And what we're now going to do is we can say, okay, I want to add up. So there's the sigma notation for sum. You might recall it from stats. You know, as you use that capital sigma. So that means the sum. So I want to add up all of these cylinders, all of those pi function x squared delta x, starting at A, going to B. But I want to look at it as that thickness is getting really close to 0. So there's my limit out the front. Now that is the integral. Right? In the same way as when we looked at area, I mean, I'm not going to prove it here because you don't need to see the proof. It's not part of the syllabus. But in the same way, if you remember, when we looked at the area one, we were able to manipulate that and show that, hey, that sum turned out to be the same as the integral of the primitive, and we end up with a primitive function. It's the same idea. It'll turn out to be the integral, and in fact, if you were to now call function x y, like I had it here, that's the formula we're used to seeing. Pi times the integral of y squared dx. Now that's where it comes from. But in extension 2, they want to see you build this. So you can't just go, oh, pi times the integral of y squared dx, and sub in. Because otherwise it'd just be a 2-net question. So in extension 2, they want to see this sort of working out where you work out what the element of the volume is by having a look at an individual slice. This line, the sum, is crucial, I guess, to the solution, because you're saying, hey, I want to sum all of these slices, but it is okay then to just jump to the next step and say, oh, okay, well that's the same as the integral. And then you go and integrate whatever you got. So about the y-axis, again, would be a similar thing then. So there's the curve. The slice is perpendicular to the rotation. So this time it's going horizontally. The thickness is delta y. So the thickness delta y, I want the radius, which is the x value, but I want that in terms of y. So I'd have to rearrange that formula. Y equals function x. We'd rearrange it. We'd end up with some function of y. And then it's the same sort of idea. Well, that's the area of the face. So my element of the volume would be that. I want to sum all of those slices up. And then that gets me to my integral, which I can then go and work out. So all right, let's look at the example then. So we're going to have a look at 4 minus x squared, which is, of course, our upside down parabola shifted up 4 units. There it is. And we're going to go about the x-axis. So the slice is perpendicular to the x-axis. So it's vertical there, which means the thickness I'm looking at is in terms of x. I want to do this in terms of the x value. So if I was to rotate that, there's my slice, I end up with a cylinder. The radius is the y value, but in terms of x, that's 4 minus x squared. So I know that the area of that circle would be pi times the radius squared, so pi times 4 minus x squared squared. Now whether you want to expand that out now or expand that out later, that doesn't really matter. I mean, that's up to you. But there's the element of my volume. So I'm going to sum all of those volumes. We're going from minus 2 to 2. We can still use the ideas of symmetry because we've got an even function there. So I could go 2 times 0 to 2. And I think that's what I did do with my integral. I changed it from 2 times 0 to 2. And the actual integration itself, you can see for this one's quite easy. It's just a polynomial. And that's what I mean. In extension 2, they're probably not really that interested in that integral. Oh, that's a 2-unit integral. It's more, how did you get there? Do you understand where the integration comes from? Do you understand that we're adding up each of these slices to come up with, and let's sub in 2 and 0, and then we get our volume. So I don't know how many marks a question like that would be off the top of my head, but you probably find there might only be 1 mark for working out the actual integral itself. Right, but the nice thing about that now is we can get that idea. We don't have to rotate around the x-axis or the y-axis. We can rotate around anything we like. So let's do same curve, but instead of rotating around the x-axis, I'm going to rotate around the line y equals 3. So I draw my slice in. It will therefore be important to find those points of intersection because we'll need to know the extremities of where we're slicing. There's my slice. So when I draw it, the radius is no longer the y value. The radius would be y minus 3. Because it's going to be the y value minus 3. Essentially, if you think back to areas, what did we say? We said top boundary minus bottom boundary. That's what I'm doing here. The y value of the red curve minus the y value of the blue curve. Well, the blue curve in this case is a constant 3. So it's y minus 3. So top curve minus bottom curve, whatever the slice is going between. And then I can tidy that up. So it's just 1 minus x squared is what I'm going to use for a radius here. And then the question becomes the same. Pi times the radius squared for the area, times it by the delta x to get the volume element. And we're summing, but we're going from, we want x values, so minus 1 to 1. And then we'll integrate that. Again, I can make use of symmetry for this one. And subbing in, there's my answer. So whenever we're working out the radius of the slice, it's the top curve minus the bottom curve. Now, if you think about it, that's what you've always done. It's just that normally the bottom curve was the x-axis, which has a y value of 0, so you didn't bother saying, top one minus bottom one, because it was minus 0, so it was cancelling out. But again, this idea transfers through. But the nice thing here is we can get some really good shapes as well. We don't necessarily have to have a disk, or something like this. If I get y equals x squared, there's y equals x squared. X equals y squared, which is the parabola on its side. The area between these two curves is going to be rotated around the y-axis. So the slice is perpendicular to the y-axis. Point of intersection of those two curves is 1, 1. There's my slice, that little horizontal bit. And when I rotate that, I'm not going to get a cylinder. I'm going to get a cylinder with a hole in it, or what we call a washer. And if you think of bolts, they have a washer on them, and that's essentially what we've got there. So the thickness is delta y. We've got to work out what is the outside radius. So the top curve would have a radius of, we want it in terms of y, so it'll be y to the power of a half. The bottom curve, the blue one, we know that it's going to be y squared. So it's going to be the top one squared, in this case y to the half squared minus y squared squared. And then the rest is we can expand out and do our sum. Now the sum is going from 0 to 1. Remember, it's y values, so we're going from the bottom where they meet, so the y value there is 0, up to the point of intersection, so it's 0 to 1. And again, the integration itself's not too bad for this one. And there we go, 3 pi and 10. But we're no longer restricted to just doing I just want to do a nice circle. See here I've got a washer instead, which gets a little bit more interesting, the shape. Here's one going back a fair while from an HSC. And this region here is going to be rotated around the line x equals 4. So you'll end up with, I want to call it a grommet. Do you know what I mean when I say a grommet? Have you seen, they're usually like rubbery, and you find them when you're putting bolts and things through, but it gives it a bit more push. So rather than a metal cylinder washer, it's sort of like, you say, I suppose another way of thinking about it is, you know those thumbtacks, the colourful ones with the blue thing, but with a hole in it. This will have a hole in the middle of it. Could be something like that. Okay, so let's have a look what they're telling us. They've given us all the equations of the different boundaries there. They've told us there's the slice. So we're going perpendicular to the rotation, which is x equals 4. That's nice of them. They've actually told us what the area is, but we've got to show that we can work that out. So there it is. I need to work out the outside radius, which I've called capital R, and the inside radius, which I've called little r. So let's go back to this shape and work it out. The inside radius. Well, the inside radius is just going to be the constant value of 3. Because if you look at the boundaries, I'm going from 4, because that's x equals 4, to x equals 1, so top minus the bottom, 4 minus 1, it'll always be 3. So that's my little radius. Now, my outside radius. It's going to be 4, but then I'm going to have to add on this little bit here. But you'll notice I've actually subtracted it. And that's where, hang on, but you've added this extra bit on. But of course over there they're negative numbers. Minus minus would be a plus. Hang on, that can get very confusing. So that's why I just keep thinking about it of top minus bottom. 4 minus whatever the x value is. 4 minus whatever the x value is. And then because the x value happens to be negative, we'll get a bigger number than 4. If I sub in, x would equal minus y squared. So I've got 4 plus y squared for that outside radius. So rather than looking at it and going, oh gee, I'm adding this bit on, just think of it, top minus bottom, and we should be okay then. Alright, let's sub those in. There's my big radius, 4 plus y squared. My little radius of 3. So my area function will be the big circle minus the little circle. We can tidy that up algebraically, and we've shown what they've asked us to show. Okay, hence find the volume. Alright, well I know that's the area, so if I multiply it by the thickness, I'll get the volume element. I want to add up all those elements, and I'm going from a y value of minus 1 to positive 1. I once again have a symmetrical shape if you look at it, so I could again go, oh well that's twice from 0 to 1. And the actual integration itself is a nice polynomial. And there's our answer. Alrighty. So from the Cambridge, but also there's some from Patel. Be warned, the Patel exercises, I've deliberately picked questions, some of them where actually it would be better to use a different method, which we'll look at tomorrow, but just to highlight how, hey, if we use the wrong method, it'll come up with the right answer, but it could involve more working out. Now, I'm not going to tell you which ones they are. You might work it out yourself, but I've deliberately picked some there for that reason.